All right, so I just needed 5 more minutes in class today, so I just wanted to do a quick review of where we were when class was over, and then finish up the information from the slides that I had for today. So if you remember where we were at the end of class, is I had gone over some simple rules of how different types of forces and couples would influence the shear force diagrams and the bending moment diagrams. What we found is if a point force, a force acting at a very specific point on a beam, what that does is it produces a discontinuity in the shear force diagram in the direction of the force and with the same magnitude. So if we look at this picture here, this is a nice demo here because we had a force, it was vertical, and here was vertical, and it had a magnitude of F, and so what we found was the shear force diagram had a value before we hit the force, and then the discontinuity in the shear force diagram was equal to the magnitude and the direction of the applied force. It doesn't really cause a change in the bending moment diagram, but there probably will be a change because of the fact that the shear force diagram changes. There will be a change in the bending moment diagram, but there won't be a discontinuity. What we found when the beam was subjected to a couple is there's a discontinuity in the bending moment diagram, but the interesting thing here is that the discontinuity has the opposite sense of the direction of the couple that was applied. So in this picture, the couple that is acting on the beam has a positive direction. It's counterclockwise. It doesn't affect the shear force diagram at all, but there is a discontinuity in the bending moment diagram, but it is in the opposite sense. See that there's a drop, even though that the couple that was producing it was positive. So that's something that we have to remember as well. So those are some simple rules. And then I thought that we could just look at this picture really quick and see what's going to happen in this situation. Like, could I sketch really quickly the bending moment diagram and the shear force diagram for this beam? It's stuck into the wall, so we're going to have to look at those forces of support forces that are acting there. So we have, let's just call this AY, AX, and MA. So if we apply our equations of equilibrium, the forces in the x direction are 0, so AX is 0, and the forces in the y direction are 0, so we have 50 positive, 50 negative, plus AY. So this is one of those interesting situations where we have AY is equal to 0. Didn't expect that. Let's look at the moments about, let's say, the left-hand side. And that's going to eliminate that's going to be my pivot point. That's going to eliminate the 50-pound force right there. So the first force that has a moment is the one in the middle. So that's going to cause a clockwise rotation. So that's minus 50 times 4 plus the support moment because the beam is embedded in the wall, which prevents rotation. And so MA is equal to 200 pound-feet. Now, if I wanted to draw the shear force diagrams, I could just use my rules about applied forces here that I see acting on this beam. So at the very left-hand border, there's a force of 50 pounds that's upward. And so we're going to start off this diagram at 50 pounds. And nothing happens for the first 4 feet because there's no other forces. Then we have a 50-pound force downward. That causes this discontinuity, a drop in the same direction. It goes down. That brings us to 0, and that's where we remain until the end of the beam, and, well, nothing really changes. So this kind of ends up looking like a step function. Now, what Chris had pointed out today in class was that he noticed that the slope of the bending moment diagram was equal to the shear force. So for the first 4 feet, the shear force has a value of 50, which means that the slope of this diagram is going to be 50. So at 4 feet, it's going to go up to a value of 200. And then the value of the shear force after 4 feet is 0. So now the slope is 0. So it's just a horizontal line. And then we get to 8 feet, and that's where the support reaction is, which has a magnitude of 200 foot-pounds, and it's positive, which means we get a jump in the negative direction that's equal to 200 foot-pounds. And that's what the diagram looks like. So you see, we didn't even really have to do any cutting of the beams or anything. We were able to just kind of draw it pretty easily. Now, kind of picking up where we left off in terms of the distributed loads, we were looking at a scenario where we had a portion of the beam and we imagined there was a distributed load acting on it that had some function W of x. The total force that would act on that little sliver of beam, which had a width of delta x, would be equal to W of x times delta x. And so we're going to do something very similar to what we were doing to find the discontinuities for force and couples. We're going to look at the forces on the left and the right, kind of add them all together, and also the forces acting on the beam. So on the left-hand side, we had a shear force that was positive. On the right-hand side, we had the shear force that would be negative and also account for any change that occurred over delta x, and that's why it's V plus delta V. And in addition, we had the force upward due to the distributed load, which was W of x times delta x. If we just rearrange this equation a little bit, we can put the W of x on one side and the shear force expressions on the other side. We take the entire equation, divide by delta x, and look at the limit as delta x goes to 0. When we do that, we notice that what we come up with is that the derivative of the shear force diagram is equal to the distributed load. And that basically means that the slope of the shear force diagram is equal to the function for the distributed load. Now, what I had mentioned in class, and we have to be careful with, is that they use the sign convention here. W is positive because it's pointing up in the picture. Notice it was pointing up. Of course, our distributed loads are almost always going to be pointing down, which means that these values will be usually negative values. Now look at what might happen to the bending moment. What value do we have? What effect does the bending moment, what effect does the distributed load have on the bending moment? So let's look at the total moments in this picture are equal to 0. We're going to do the moments about 0.0, which is on the right-hand side. We have minus m over here, and then we have minus v times delta x, and so that's this force right here creates a moment about this point equal to its force times delta x. Both of these are negative. Then we have the force of the distributed load is also going to be negative. The total force is W of x times delta x, and the distance that it's at is k delta x. And so the way that they're doing that is they're saying, of course, we have to put the distributed load force somewhere along the length of that, or the width of delta x. We don't know exactly where it is. It's going to be, If it was uniform, it would be right in the middle. If it was a triangle, it would be shifted towards the right-hand side. So K just represents an arbitrary fraction, that it's at, some fraction of the total length away from the right-hand side. So we're just trying to be super general in this case. And then the last moment we have is the moment on the right-hand side, m plus delta m. And this all adds up to be 0. So if I just sort of collect some like terms, I have delta m, because the m's are actually going to cancel out, minus v delta x minus w of x times k times delta x, that quantity squared, equals 0. So I'm going to rearrange this kind of like I did before for the shear force diagram. I have delta m on one side, and everything else I'm going to put on the other side. Then I'm going to divide everything by delta x and take the entire limit of this as delta x goes to 0. The left-hand side ends up being the derivative of the bending moment with respect to x. And then on the right-hand side, we just get v, because this term will go to 0, because it will be, when we divide by a delta x, we'll be left with a delta x on top, which is going to make that entire term equal 0. So here what we find is the slope of the bending moment is equal to the shear force value. So the idea is we are going to use the distributed load is going to help us find the shear force diagram. And once we know that, that shear force value, that functional relationship, is going to allow us to find the slope of the bending moment. And furthermore, you can do an integration, rearrange this, and write that the integral of dm is going to be v dx. And so you could actually come up with an expression for the bending moment, like a functional relationship. So we're going to look at this problem where we have a relatively simple distributed load. It's uniform, nice and constant. So I'm going to go to a smaller picture. We're going to draw or label the forces that are acting here. So at the wall, I have an AX, I have an AY, and I'm going to have the M sub A. And then, of course, the force that is equivalent to the distributed load, which is going to be 4 times 6, is going to be located 3 meters away from the end, because it's going to be right in the center, because it's a real simple rectangle. So let's look at our equations of equilibrium just to find these support reactions, because these will influence the shear force diagram and also the bending moment diagram as well. And so what I did is I was able to figure out what the reaction is at the wall, both for the vertical force and the couple or the moment at A. I found those values. Now what I'm going to do is I'm going to try to sketch the shear force diagram first. So I'm going to do V as a function of x, and what I'm going to remember is dv dx, the slope of this is equal to the distributed load, which for us is minus 4. It's minus because it's pointing down. And so what we're saying is that the slope of the shear force diagram is going to be -4. Now, first, we have to keep in mind that there's a force right at the left-hand side, which is equal to the support reaction, which has a magnitude of 24 kilonewtons. So we're going to start the diagram up at 24, and then it has a slope of -4. And if we do the calculation, what that slope is going to bring us back down to 0 when we get to the end or the right-hand side of that beam. So that's not too bad. The graph of this is 24 minus 4x. And then here we're going to look at the bending moment diagram. Now this one is kind of interesting because it's actually going to start off with a negative value because there's a positive moment at the left-hand side. Remember, that's going to make this graph jump down an amount of 72 because the discontinuity or the jump is opposite the sense of the actual moment itself. And then the integral is the slope is the integral of v dx, which is going to be equal to 24 minus 4x dx. And so if we integrate this, that's going to give us 24x minus 2x squared. And we're going to start off, it starts off at minus 72, so that's our constant, plus 24 minus 2x squared. So essentially it's sort of parabolic with a concave down function. And if we check the value of m at x equals 6, we're actually going to get 0. And so, which is usually the case, it's going to come back down to 0 at the ends. So it's just kind of like this upside down parabola that goes to 0 at x equals 6 meters. And so that's just sort of an example of how you can sketch these diagrams pretty simply using the information that we know about how everything is related. You know, what do point forces do? What do couples do? How is the shear force diagram related to the distributed load? And also, how is the bending moment diagram related to the shear force? Just so you know, even if there's no distributed load, if that is actually equal to 0 because it doesn't exist, that just tells you that the slope of the shear force diagram at that location is 0. It's just a horizontal line. And so we can use these relationships with the shear force diagram, the V and the M that we see here, even if there isn't a distributed load.